And we move out, we see the inner planets, that's the Earth passing by. We're then going by Jupiter, Saturn is coming up. Saturn, Uranus in that orbit, and that was Neptune, I think. And so that's the edge, that was Neptune, that's the edge of, pretty much the edge of our solar system. And so here is a family portrait of our solar system, not to size, but we have the Sun, Mercury, Venus, the Earth, Mars, Jupiter, Saturn, Uranus and Pluto. Uranus and Neptune. Pluto, you may have heard of, was a planet until 2003, when the International Astronomical Union decided it was no longer a planet. I agree with that, Matt. I also don't like that. I think, you know, it's a cultural thing, and I think Pluto should have been a planet, but it is no longer. I was actually at that meeting. It's a 2-week meeting. I was there for the first week, so I didn't get to vote in the second week. So I was very proud.
Why did they make that decision?
They made that decision because they had discovered a few additional bodies that were bigger than Pluto, beyond the orbit of Pluto. So the question was, do we need to make them planets as well? And then there was like Sedna and some other objects. Or should we demote Pluto based on some scientific principles? And they decided on that option. They call it dwarf planet now. Here is a similar family portrait of the solar system, but now to scale. And you can see the inner planet, the rocky planets are very small compared to the outer gas giants. You can see Saturn is a bit smaller than Jupiter as well, also in terms of mass. Mass is weight, right? This is what it looks like, what the solar system looks like from where the current most distant satellite is, the Voyager. And that's what the Earth looks like. So that's where we are. It's a very fragile little body in the universe, so we have to be careful of it. I'd like to take you a bit further than the planets, because that's not it, of course. Right? We go out from the sun again into the solar system. And now beyond the last planet, we start to see a whole bit of fuzzy material. We'll start to talk about that in a moment. But what we also see is that it looks like the sun and the planets around it are moving around our Milky Way galaxy. And while they do that, they push gas out of the way. So you get here a higher density of gas going forward. It's like a bow shock on a boat. Here's the reference to the Maritime Museum. But this is, it's a bow shock, but it's like a higher density of hydrogen gas that we find everywhere in our Milky Way galaxy. So the solar system actually moves around the galaxy, Milky Way galaxy. It takes about 300 million years to go around once. So let's go back to our steps. Step 15. 1 petameter on the side. We have the sun, and that is it. There is nothing else. Space is very, very empty. This was, it said, so light requires just over a month to cross this picture. And really what's in that, give me a moment, really what's in that volume are icy bodies, rocky and icy bodies, far beyond the planets in our solar system that occasionally get close to each other. Their orbits might be disturbed and they might plunge into the center of the solar system. Well, what happens when ice gets warm? It starts to evaporate. So what do we get to see? We get to see comets. So comets come from those distances in the outer solar system, plunging into the inner solar system, evaporating their tails. The tails are always pointing away from the sun, by the way. And this is an artist's impression of what those rocky and icy bodies might look like. There was a question there.
It confused me. You said that there was a bow wave of gases being pushed around.
Yeah.
And then you said, oh, space is empty.
Okay, space is very empty. The density of hydrogen atoms in the universe is better than any vacuum we can, it's lower than any vacuum we can make on Earth. So it's really, really empty, but it's not absolutely empty. There are hydrogen atoms floating around. And because of the enormous scales that we're talking about, there is enough hydrogen to form this bow shock. Yeah. Okay, step 16. 1 light year on the side, in 3 dimensions as well, of course. 10 petameters. There is nothing else. The nearest star is about 4 light years away. Alpha Centauri, Proxima Centauri. So this inspired Douglas Adams, The Hitchhiker's Guide to the Galaxy, to write, as his opening paragraph of that book, Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts. And then he starts the rest of the book. If you haven't read it, there's a great film as well. It's funny. Have a read or have a look. Have a look. Step 17. 100 petameters, 10 light years on the side, and now we start to see the nearest stars. Within this volume of space, 3 dimensions, right, there might be, what did I say here? About 11 known stars. And the sun is weird in the sense that the sun has no companion. All of the other stars in this volume of space have a companion. They're called binary stars. Or they are red dwarf stars, which are too small to really have a second companion. This is us in the middle, and that's, in 3 dimensions where the other stars are located. Very few stars. Step 18. 100 light years on the side, or an exameter. And now you get to see a lot more stars, but they're all in the background. We start to see our Milky Way galaxy. Our Milky Way is a massive conglomeration of stars. And I won't bother you with the number because they're mind-bogglingly large numbers. In this volume there are maybe 1,000 stars within 50 light years of the sun, but there are many more in the background. But what's perhaps more interesting is how many of those stars have planets. I gave a public lecture to an amateur astronomical society on Monday, and I did talk about some planets. I showed a movie made in 2022 when we had found 5,005 planets orbiting other stars. I was at a conference today at Macquarie Uni, and one of the speakers showed an up-to-date number. 5,800 planets are known to orbit other stars. Most of them much bigger than the Earth, because it's very, very hard to find planets as small as the Earth. Here is a movie that shows you the compilation of about 3,000 of those planets orbiting around their stars. We're using the same star here for all 3,000, so you can see how many there are. Hopefully you don't get dizzy. So that's the central star. Planets going around it. And when we zoom out, you see that most of the planets that we have found are actually located very, very close to their star, not very far away. I'll wait till it zooms out a bit. Now the problem with having a planet so close to the star is that if you have an atmosphere, it's very easy for the star to strip off the atmosphere, so it's not healthy for life. So those planets are not good targets to look for life. How do you look for planets? There's a lot of different ways of doing it, and here's one of them. When you have a star and you have a planet going around it, both of them have a bit of gravity. So even though the star is much bigger than the planet still tugs a little bit on its star. So that star will wobble a little bit on the sky, and with good instruments we can actually measure that. Amazingly, we can do that. Or we can look at stars over time and take pictures and see how bright they are, and at some point suddenly that brightness might dim a little bit. And that shows you also that a planet might have come in front of the star. Of course, that requires that the orbit of that planet must be located such that we can actually see it across the star. Right? So that limits what we call the inclination. And so this is the way that works. Right? So if we have a planet going around the star, at some point that intensity dips, and you can see that might be an indication of a planet going around that star. Or perhaps we can look at places where stars are being born, because in visible light and even in infrared images, they look dark. And here are some real pictures taken with the Hubble Space Telescope of actively star-forming and planet-forming regions. Young stars with dark patches around them. These are called debris disks, which eventually turn into planets like we have in our solar system. So there's a range of ways in which we can look for planets orbiting other stars. We go to step 19 now. This is 1,000 light years on the side, and now we get to see our spiral, a part of our spiral arm. The Milky Way is a spiral galaxy. The Sun is just one of its many, many stars located somewhere in the suburbs in one of the spiral arms. I won't bother you with this so much, but this is what we think the Milky Way looks like on the top. You can't fly out of the Milky Way to actually take a picture like that. Central bulge, central concentration, beautiful spiral arms, and the Sun is sitting somewhere in the outer regions. If you look at the Milky Way from the side, and we can do that because we're inside of the Milky Way, we take a picture of the whole sky, and that's what it looks like. This is an actual picture of the whole Milky Way from inside, with the central concentration, the bulge, and then the disk, and the disk is red, because in the disk we have this dark laying of dust. Dust is the same kind of stuff that you find under your bed if you don't vacuum enough. Right? It's carbon-based particles, soot. And that makes light appear redder. I can tell you why that's boring. If you look at the very center of the Milky Way, this is a picture, a combination of the Hubble, the James Webb, and the Chandra satellites. Hubble in visible light, James Webb in infrared, and Chandra in X-rays. In the very center of the Milky Way, we have a little spiral structure, and right in that very center, we have a black hole. A black hole that's about 3 million times our Sun. 3 million times. Far enough away that we don't have to worry about it, so don't worry. That's the center of our Milky Way. Step 20, 10,000 light years on the side. We're inside our spiral arm here. We're just moving on. Step 21, a zeta meter, 100,000 light years on the side, and now we get to see most of our Milky Way galaxy. Now the Milky Way is a beautiful spiral. It's what we call a typical spiral. Typical because it's the best one we know, not because it's typical. And there are many, many galaxies around the Milky Way. Then the Sun goes around the Milky Way. Since its formation, it has gone around the Milky Way between 15 and 18 times only. So it takes a long time, 250, 300 million years. Okay, I'm going to play a brief video that explains a bit more about the structure of our Milky Way.